Hello students, welcome back. Let us resume our discussion in section 3. We went through these two. Now let's do one more. Again, do you recognize this problem? You should. You saw it right here. So I'm not going to do method number 1. Method number 1 follows this very problem here and then apply the fundamental theorem. Plug in x equals 1 and x equal to 0 and subtract one from the other, and that's it. So I'll use only second method. And then that begins with a substitution of the inside as before. And then let's do the derivative computation. Okay, there you go. That's the inside, substitution number 1, and that's dx, substitution number 2. Okay, let's go ahead and copy and paste this. And then let's find this out. But before that, we have to make sure that the intervals are taken care of as well. Can you read this 0,1? Okay, all right, can you read it? Even bigger font? No, that's too big. Okay, all right. What happens at x equals to 1? U is 1 plus 0 squared. U is 1. All right, that's the starting point. What if x equals to 1? Then U is 1 plus 1 squared, so U is 2. So that's the ending point, purple. So this entire integral becomes, let's see, this is U, and this one is okay, like this, 1 over 2x du, and then x cubed is still there. So we need some further work. Okay, x squared, now this x is gone, and then this 1/2. So let's rewrite like this. Okay, but we still need some work. You see, I still have x squared here. And this x squared is u minus 1. So here, u minus 1. And that'll complete the substitution. By the way, I don't need these colorings for these. Oops. Okay. Now x is running from 0 to 1, and u is running from 1 to 2. So let's change this. U is running from 1 to 2. Yeah, u is running from 1 to 2. Okay, as for the final computation, okay, all right. U is running from 1 to 2, and then 1/2 u times square root of u, so u to the 3/2 power minus u to the just 1/2 power, square root of u times 1. So if you use the power form, you can rewrite like this. And therefore, you're going to get the antiderivative computation like this. Add 1 to the power, and then divide. Add 1 to the power, and then divide. And that's going from 1 to 2. Is everything okay so far? Plug in u equals to 2, then I'm gonna get, let's see, 1/2, 2/5 cancel out, 1/5, and then 2 to the 5/2 power, and then 1/3, 2 to the 3/2 power, and then plug in 1, 1/5, 1 to the 3/2 power, 1/3, 1 to the 1/2 power. I don't know whether it's meaningful to simplify this thing anymore, but let's see. If I do that, 1/5 doesn't go anywhere, and then this is square root of 2, 2 to the 4, so 4 times square root of 2. Minus 1/3, and then that's 2 square root of 2, 1/5 plus 1/3. Yeah, I guess that's it, and then some further simplification. Oh my, I got tired of it. Let me ask Mathematica to simplify this. And then you're gonna get 2/15 plus 2 square root of 2 over 15. Yeah, I believe you. I mean, common denominator 5 times 3 is 15 after all, and then we have those square root of 2's. Okay, that makes sense. And as for all those computation, okay, now that I'm looking at the answer key, I mean the final answer by Mathematica, I'm convinced that I did it right. But still, let's check that with the answer key here. What did I do? Yeah, that's right, correct computation. And then if you use method number 1, you can use this integration technique, the very same thing that we did in section 2, and then the net change. So these are the kind of things that you'll have to do for the definite interval problems. I have a couple more, and definite integrals for area computation problem. Here's another. And in this kind of problem, you'll have to calculate the definite integral of this function, not from -1 to +1, because if I do that, then you're going to get 0, because positive and negative part will cancel each other out. So either you do this from -1 to 0 and 0 to 1, and then get positive values and add them up, or just find out the integral from 0 to 1, this part, the right-hand side part, and thus double it. Same thing here. Calculate only this part, the definite interval from 0 to 1 of this, and then double it. If you do that, you're going to get this kind of definite integral computation. Apparently, I use the second method. And then if you follow through, you're going to get the area, geometric area. Same goes for this. Even though you have an area problem, it's just a definite integral problem. From 0 to 1, get this, and then just double it. Not from -1 to +1 all the way. You're going to get 0 if you do that. Oops. So that's the setup. And then you can use the integration by substitution. And then we end up with this kind of area computation. In fact, this is the very same problem we just did, isn't it? No, not really. That is actually the same. Okay, so much for lesson 13. That pretty much concludes Calculus 1. I have one more planned, and that's mainly an optional topic. I'm going to talk about some advanced theory of Riemann sums, but otherwise we are done with Calculus 1.